Firstly, actually, I wanted to say thanks to Angie and the team. This has been an awesome event so far. It's really good to see the community getting together and so many interesting stories being told by some people that are our customers and partners that we work with. So really appreciate everyone taking the time to come here and really appreciate the work that Angie and the team have done. So just congratulations to everyone. Thank you. As Angie said, my name is Mitch. I'm a solutions architect and I work for AWS. I was trying to think of something interesting that I could share with you about myself. And the only thing that's really interesting and that's been relevant to me for the last few months has been this. I'm a big Liverpool fan. This weekend, we're about to go into one of the biggest games of the season and of the last few years for us as well. Any other Liverpool fans in the audience? Okay. Any Real Madrid fans in the audience? Okay, fair enough. Nice. We'll have a chat later. But yeah, that's a big event for me. So my whole family is behind me on this. It's very exciting. Really looking forward to seeing what happens this weekend. As Angie said, one of the most exciting announcements that came out recently for us, for a lot of people that are interested in this space, is Amazon EKS, or Elastic Container Service for Kubernetes. We announced that at our reInvent conference in 2017. So it's a managed Kubernetes service, and the goal of the service is to make it easy for our customers, many of whom are probably in this room today, to run and deploy Kubernetes clusters on top of AWS. We take away a lot of that heavy lifting that's typically associated with managing those clusters, installing and configuring software. So under the covers, what is it we're doing? We're actually building a multi-master, highly available Kubernetes control plane for you. We're integrating it with Identity and Access Management Services, or IAM, to make sure that all of the authentication requests for your API calls are gated through IAM as well. We're taking care of the management of the underlying data store for Kubernetes, so etcd. Who loves managing etcd clusters? Ah, nice. Greg, excellent. We'll talk after. But yeah, the goal of the service is really to make it much easier for you to deploy your applications using Kubernetes on top of AWS. As part of the project, a lot of exciting initiatives came out. Obviously, we had a lot of customers running Kubernetes on top of AWS already. Just out of curiosity, by way of show of hands, who's running Kubernetes on AWS at the minute? Interested to see? Okay, cool, fantastic, great. Given that there was a lot of people already using Kubernetes on top of AWS, there was a lot of activity in the open source community. And you may have seen that we became members of the CNCF in the middle of last year, which was great. We got to take part in a lot of the discussions around the direction of some of the projects that are happening there. And we got to take the feedback that we got from our customers into the CNCF and help maybe shape the direction of some of the projects that are in the incubator stage of the CNCF lifecycle. Lots of open source projects out in the ecosystem at the minute, and one that particularly resonated with us based on some feedback that we got with customers was CNI, or the Container Networking Interface. Now, I'm not going to dive too deeply into CNI just yet. What I want to start by doing is just taking a step back and having a look at container networking and some Container Networking 101. So how do we network containers? Well, this is basic networking here. We've got a process running on an EC2 instance. That process is bound to an Ethernet adapter or an Elastic Network Interface in VPC parlance. We have a route table. We've got some firewall rules implemented through something like NetFilter and IP tables. And then we have a local host interface as well. This is typically what we see on a server when we're running a process on an operating system. If we take a step back, that actually sits inside of what we call the default or the global namespace. And what we see there, each of those components makes up our network stack. Now, if we introduce containers into the mix, here we have another instance of our HTTPD process. It's running in its own new isolated network namespace. It has its own copy of that network stack as well. So you can see, again, we've got firewall rules, we've got a local host interface, and we've got routing rules. But we've got a situation now where we've got this process sitting in isolation thanks to namespaces, but it can't really do much. It's not able to talk to the outside world. So then the solution to that problem is to build or create what we call a virtual Ethernet pair, or VETH, is the abbreviation we typically use. That VETH pair has one arm in the global namespace and one arm dropped into the container namespace. And the traffic then flows through that pair, essentially just like an Ethernet cable connecting two ends. And the traffic flows through there into something else, which in this case is a bridge adapter. It could be other things as well. And then ultimately the traffic gets moved out into the outside world. That's a lot of work that someone has to do from a configuration perspective, and it is quite complicated. Obviously, every time we deploy a container, it's not something that we'd like to spend time doing. It's not very efficient. Containers are meant to give us the flexibility and the agility that we need to release software quickly. So, there's a lot of challenges managing those namespaces and the container networking models that need to be constructed. And as you can see here, it is complex, but the feeling was that Kubernetes could help us solve some of that problems and help customers solve some of that problems. And whilst that's kind of true, it's not strictly true. There's a few considerations that we have to take into account. They are the core kind of fundamental requirements or fundamental principles of Kubernetes networking. I'm sure many of you that have read the documentation will be familiar with these principles. All of those containers need to be able to communicate with one another without using network address translation. All of the nodes within the cluster need to be able to communicate with the containers as well, and vice versa, also without using network address translation. An IP address that the container itself has and sees itself as having needs to be the same IP address that other containers within the cluster see it as having. So they're the principles of Kubernetes networking. How do we solve that? Well, Kubernetes has a number of different networking provider options that help us solve that problem and allow us to meet those fundamental requirements of Kubernetes. Who's used KubeNet before? Anyone deployed a cluster with KubeNet? Yep, so KubeNet's one of the default options out there today. CNI is one of the more common ones. I think a lot of people are using CNI. KubeNet is very basic in functionality, but it's extremely performant, and its simplicity is probably one of its benefits. It has some limitations in that we can typically only grow a cluster to a certain size of nodes, given the way that it handles packet routing, traffic routing, sorry. CNI, most of the CNI options out there today offer more advanced functionality. Typically, the CNI providers out there implement some kind of overlay network to help us meet the requirement of giving each pod its own IP address. Some of them don't. Calico is a common example that doesn't implement an overlay network. But even Calico, in some cases, if you're wanting to pass traffic across an availability zone domain, then you also need to implement some overlay or encapsulation there to make that happen as well. But Calico and Flannel and Canal and some of these other popular CNI providers that are out there today implement additional capabilities over and above what's typically there with the KubeNet solution. But the feedback that we got from our customers was around those solutions being absolutely great, and they solve a real problem. But there are some challenges with them. Primarily observability, especially if we're using overlay networks, can be quite difficult to actually see what's going on because the packets themselves get encapsulated as they move through the network path. And also, in some cases, high volumes, network performance can be impacted slightly by the constant encapsulation and de-encapsulation of the packets as they move across the overlay network. And as I mentioned before, KubeNet itself has a limitation of a number of nodes that we can deploy within a cluster. But we thought CNI is the way to go. It's the standard specification that's been created to help abstract away the complexities of wiring container networking to real-world networking. So that's really what we want to focus our time and effort. It's an open source solution, so it marries to our initiative around embracing open source for the EKS project that we're developing. So let's take a quick check of what CNI is for those of you that don't know. First and foremost, it's a specification or a standards-based specification that we use for configuring container networking. There's a number of different components that are in play when we invoke a CNI plugin. There is the runtime itself. So in the case of Kubernetes, the runtime is the kubelet. That kubelet then invokes this plugin, which is the CNI component that we've developed in the instance of the VPC CNI plugin. That plugin gets invoked, and that plugin takes responsibility away from Kubernetes for configuring things like the virtual Ethernet pairs that I showed before, allocating the IP addresses to the containers, configuring the routing rules and the IP tables configurations that need to be in place for that container to be able to communicate with other containers in the network, but also the rest of the network itself. All of that information and the configuration for the runtime, for the plugin is actually read in through a configuration file as well, which is typically written in JSON and dropped on the file system of the host that's running Kubernetes. So what does the VPC plugin that we've created look like, and how is it different to some of the models that are out there today, specifically things like Calico and Flannel? So here we've got an example of two EC2 instances deployed within a VPC. We can see the subnet there at the bottom. We've got the CNI plugin deployed onto those EC2 instances, and we're going to provision a pod. Each of those EC2 instances also has an elastic network interface connected to it. As we provision those pods, we're going to do, the CNI plugin is going to go and reach out to the VPC control plane and say, I need some IP addresses for the pods that are there. What it's going to do is it's going to go and pull back a range of IP addresses or a pool of IP addresses and allocate those to the interface that we have connected in the form of secondary IP addresses. It's going to then allocate those secondary IP addresses to the pods that get provisioned, and the CNI plugin takes care of that process for us. All of those pods will ultimately end up getting a fully native VPC routable IP address, essentially turning the pods into another EC2 instance connected to the network. Maximum performance across the VPC because there's no encapsulation. Visibility if we were to use network capture tools because there's no encapsulation as well. So what is the plugin? It's a native networking capability for Kubernetes built around VPC. And the reason we wanted to build it around VPC and have that native integration is because a lot of our customers already know and understand VPC. They understand the principles of VPC. They're comfortable using VPC and all the constructs that wrap around VPC. So it made sense for our customers that we built this solution. It uses elastic network interfaces, as I mentioned earlier, and we allocate secondary IP addresses to those network interfaces, and I'll talk a little bit more about that very shortly. And as I mentioned, pods get these VPC routable IP addresses, which means there is no subnets allocated to entire instances. There's no overlay networks required. These are, for all intents and purposes, EC2 instances running within EC2 instances. We're bridging that gap between Kubernetes networking and the Amazon VPC. But we're not doing it at the expense of performance or overhead or too much machinery in the way. So this is a really thin layer. And this is true for all of the other CNI plugins that are out there for the most part as well. The CNI plugin, the goal of the project is to be a thin layer to facilitate the network connection and the wiring up. And then it's going to step out of the way and it's going to hand everything back to Kubernetes in terms of instantiating the pods that need to be created. So there should be little to no impact. And from a performance perspective, because once we've wired up the networking, we get completely out of the way. We get out the path of the data, and the packets just move on to the underlying VPC fabric as well. And the pod IP address, as I mentioned before, essentially becomes the secondary IP address that's connected to the ENI, which we have attached to the EC2 instance. So where can we use this CNI plugin? Any Kubernetes cluster that's running on AWS. So you can deploy it. It's by default. When we create clusters using Elastic Container Service for Kubernetes, or EKS, that is the default and only network provider that is currently supported. If you were to provision clusters using COPS, for example, or Kubernetes, the hard way approach to deploying Kubernetes clusters, once again, you'd be able to deploy that CNI plugin. It's CNI. It's compatible with any other orchestration tool that also supports the CNI framework, which is one of the other reasons that we decided to go down the path of using CNI. How does it get deployed? Very easily, extremely easily. One of the goals of Kubernetes is to abstract away the complexity and the implementations of details of what sits under the platform itself. We want to make it easy for people to consume the service and deploy applications on top of that service. And the deployment approach for the CNI plugin is equally as straightforward. We deploy it as a daemon set, and most of the other CNI plugins are deployed in a similar way. Here's an example. I was going to bring up a demo and do it for you, but I wasn't feeling the demo gods on my side today, so I just decided to go play it safe and go with a screenshot. So here it is, though. We've got a daemon set deployed. Here I've got 3 nodes, so we deploy an instance of the CNI plugin onto each node. What does it look like under the covers? Well, let's have a quick look here. We can see that we've got the EC2 instance running. We've got the CNI plugin running within the EC2 instance. We have the kubelet itself. When it's asked to start a pod, it will invoke the CNI plugin. The CNI plugin then takes responsibility for wiring up all of the networking within that pod, creating the VETH pairs, configuring the routing tables, assigning all the IP addresses, and then getting out of the way completely. At which point then, the pods that have been provisioned will be able to route traffic to the outside world, and pods running on other nodes within the cluster will be able to route traffic back into that pod. More interestingly, again, because this is essentially just another EC2 instance running on your network, a lot of the abstractions are removed away. Other EC2 instances that are sitting outside of the cluster can directly access those endpoints as well, which could make some interesting application models and patterns in the future. The VPC plugin itself, the CNI plugin itself, my apologies, it isn't just one component. We don't just have a CNI binary sitting there. The CNI binary is part of it, but we also have a long-running daemon process, which we call IPAMD, or the IP Address Manager Daemon Service. That service runs as a long-running daemon, as I mentioned, on the instance. And the job of that service, or that binary, is to observe the state of the node from a network IP address perspective, an elastic network interface perspective, and identify when it needs to go and connect more elastic network interfaces to the node, because there has been an increase in the number of pods that need to be provisioned. Now remember, I mentioned that we use secondary IP addresses for the pods that we deploy. Those of you that are familiar with EC2 will be aware that EC2 instances have a limit on the number of ENIs that can be connected, and they also have a limit on the number of secondary IP addresses that can be attached to those ENIs. And that's the job of the control plane, or the IPAMD binary that I've got here. It's to make sure that if at any point we fall below a threshold, we are able to go out and connect another ENI, allocate a new pool of secondary IP addresses to maximize the performance of pod startup times. Let's have a look at the packet flow here as an example of a pod being instantiated on a node and how the traffic moves across the cluster when we do that. So the kubelet itself calls the CNI plugin and asks it to set up the network for a new pod. So here we've got the pod, the default namespace at the top, and we've got a pod namespace at the bottom. Currently nothing within that pod namespace. First job of the CNI plugin is to create the virtual Ethernet pairs. It's then going to take one of those virtual Ethernet pairs, one of the end of that virtual Ethernet pair, one end, and connect it in to the pod namespace, at which point then it's going to wire together those two ends, and it's then going to configure some routing rules to make sure that the pod itself, or the container that's running within the pod, knows how to get out of its own local network space and into the outside world. So it configures some routing rules there to say this is the path you need to take to get to the default namespace, and once you're in the default namespace, then we'll pass you off onto the elastic network interface that's connected to the instance, and packets will just flow out onto the VPC. Once that connection's been made to the ENI, the packets can then flow natively across the VPC fabric over to a corresponding node on the other side with a very similar setup. And again, as I mentioned before, very similar in terms of packet flow and data flow as you would expect to see if you were deploying an EC2 instance and you were wanting to send packets from one end to another. I mentioned briefly as well that one of the other benefits of this approach to networking within Kubernetes is that it gives us visibility into that packet flow and that data flow. So we can inject tools like here I've talked VPC flow logs, which is our managed log capturing service, traffic analysis service, sorry. In addition to that, there are plenty of other tools that you could wire into your infrastructure to actually observe the packets and get much better visibility into that traffic as it moves through the VPC fabric. So that's pod-to-pod traffic flow across cluster, meets the requirement of Kubernetes. Packet flow pod to external, very similar exercise. We do something slightly different. So when I say pod to external, what I mean is traffic that is going to an address that falls outside of the CIDR range associated to the VPC. So if I were to ping Amazon.com, for example. So we do a slightly different set of configurations there to make sure that the packets know where to return back to from an outside world perspective. And obviously we have things like NAT gateways within the infrastructure to facilitate the mapping of those public addresses back into the private addresses that are attached to the ENIs. One of the questions that we get asked a lot with this model is that if you're sending all of the packets through a single elastic network interface, and you typically associate security groups with an elastic network interface. So how do I get granular about controlling the egress and ingress from the containers that I'm deploying with this model? We called some Tiger power, or Tigera power, should I say. So who's using Calico here already? Did I mention? Calico? And people using network policies through Calico? Yeah, cool, okay. Great. So Calico is pretty much the de facto standard when it comes to configuring network policies and using network policies within Kubernetes clusters. And we worked very closely with Calico as part of this implementation to integrate the Calico network policy capability with the Amazon VPC CNI for Kubernetes that we've created. So it turns out that the Calico components are quite modular. So with some simple tweaking of a few manifest files, it's easy to break out the bits that you want. And specifically, we wanted the policy part of the Calico suite of capabilities. When we deploy the CNI plugin, you can deploy it in one of two modes. The first mode is the CNI plugin on its own, which will essentially facilitate the wiring up of the networking for you. The other mode is deploy it with Calico. And it's as simple as essentially running another manifest file or having a manifest file that contains both sets of specifications. And we deploy the Calico daemon set alongside the Amazon VPC CNI daemon set. So essentially, it looks like this. Once again, I shied away from running a demo of this because the demo gods were not with me today. But here we've got the AWS node daemon set. So this is what runs the CNI plugin itself. And then we've got the Calico node daemon set. And this is the set of components that facilitate the wiring up or the programming of the IP tables rules within the instance itself to make sure that traffic rules are applied and respected when we configure them through the Kubernetes API. So what are some of the things that we need to consider about this approach? Well, I already mentioned the fact that ENIs are limited to the number, the instances have a limited number of ENIs that can be connected to them. So if you're thinking of using this particular CNI plugin, and we encourage you to definitely explore it and have a play with it, think about how that means, what that means to the number of pods that you can potentially run on the EC2 instances that you have. So there's a simple bit of maths there that you can use to work out how many pods you'll essentially be able to run. So the number of network interfaces times the number of addresses per interface minus 2, or minus the number of elastic network interfaces. The minus the number is actually because the primary network address that we assign to each ENI cannot be used and allocated to a pod because we use that for the internal routing across the veth pairs. Other things that we do. IP allocation, we spent some time working through this one, but in order to, as I mentioned before, not impede the process of creating pods at all and add any kind of delay, what we do is we create these warm pools of secondary IP addresses for you. So when a new instance comes online, we attach an ENI to it, it's going to go out and it's going to go and grab the maximum number of elastic network secondary IP addresses that can be allocated to that ENI to make sure that there is a pool of secondary IP addresses ready to go as soon as you want to start deploying pods onto the node. That's great, but it may cause you some problems in a number of scenarios. For example, perhaps you don't have a particularly big pool of IP addresses, and you're always looking to optimize the usage of those IP addresses. So the original solution, as I mentioned, was to attach all the ENIs and allocate all of the IP addresses. As of a few days ago, we actually merged a pull request, so number 68, if you're interested in going and have a look at this, that now gives us the option to go in and actually configure the number of ENIs that we pre-allocate to the node, which means that if I am a little bit more conservative about the use of my IP addresses, or I want to be more conservative, I can select that I'd like the CNI plugin, or the IPAN daemon specifically, to only allocate an additional 1 or 2 or 3 elastic network interfaces and the corresponding number of secondary IP addresses as well. And the great thing about this project, given that it's open source, is that we get lots of feedback from people that are using it, customers that are using it, and we're able to continually add new capabilities that is driven by that customer feedback. So again, I would encourage you to pop along to the GitHub project, and I'll share a link with you in a moment, to have a look at it, consider deploying it into an environment for testing and experimentation purposes, and give us some feedback and potentially open some issues or suggestions around how we might go about improving that given your specific use case or requirements for Kubernetes. So just in case you weren't listening, I know it's a bit late in the day. Everyone's quite keen to go and get some tea and coffee. What is it we're here talking about right now? It's a new CNI plugin that we've developed for Kubernetes. It's open source. The EKS service leverages a whole bunch of different open source tools, including a project by Heptio, the AWS Authenticator. Thank you. Defense in depth is an important aspect of every architecture, and in line with that, we're giving you the capability to use the Calico network policy capabilities to ensure that you can create those secure and micro-segmented architectures for your microservices applications. And then go and try it yourself. So it is in alpha. I will just throw that disclaimer out there right now. It's alpha at the minute. I wouldn't encourage you to go and deploy it into production just yet. It's moving very quickly, so expect it to move out of the alpha stage soon. But hop along to the URL I've put at the bottom there, have a look at the CNI, have a play with it, install it, deploy it, give us some feedback. We'd be really grateful to hear from you. Here's some additional links that you may want to hop along to. So the top one is the actual link to the GitHub repo for the project itself. The bottom one is a link, sorry, the middle one is a link to a table which gives you an explanation of the number of secondary IP addresses and ENIs that you can actually connect to an EC2 instance. And then the last link is a workshop that we put into GitHub as an open source initiative to help educate people about some of the best practices and ways in which you could deploy Kubernetes on AWS. Definitely worth having a look. A lot of people contributed to that, including Arun Gupta, who's our principal open source technologist. So there's some really good material in there, and one of the workshops or the labs in that is showing you how to actually set this up and configuring some of the requirements that there are for the CNI plugin. Last thing from me is this. I expect everyone to be tuning in bright and early on Sunday morning and cheering. I'm even wearing my red Converse, especially for today, because we're getting so close to the big day. Thank you very much. Appreciate your time. Please come and see myself and my colleagues over at the AWS booth if you've got any more questions, and we'll try and answer them for you. As long as the questions aren't when is EKS going to be launching and when is EKS going to be launching in Sydney. But yeah, I appreciate your time and hope you enjoy the rest of the conference. Thank you very much.